Welcome, everyone. This is CIERA's annual Astronomy Night Out. It's one of our 2 annual public lectures that we do. The other one typically occurs in the fall, usually on homecoming weekend. So watch for that. And then next spring, watch for this one again. I'm Shane Larson. I'm the Associate Director of CIERA. For those of you who don't know about CIERA, it is our Center for Interdisciplinary Astrophysics here on campus. We do all things astronomy. We do research. We train students. We do lots of public education. We do a lot of public outreach like this. And so we will have all kinds of events that we are a part of. If you were watching the slides when we started, we have other events regularly downtown, Astronomy on Tap. We have events every Friday evening. Dearborn Observatory here on campus is open. And on the last Friday of every month, we have astronomers there who will answer every question you have about black holes and, cosmology and whatever suits your fancy when you want to come talk to us. So if you're interested in astronomy, if you have someone in your family who has that astronomy bug, there's certainly opportunities to join us. You can find all the information about our events on our website, and you can certainly join our mailing list and get that information in your mailbox. Okay? So tonight, the way this event works, we will have a lecture. I will introduce Caitlin in a moment. After the event, there will be activities, which many of you saw in the space outside the hall, as well as in the classroom across the way. There will be CIERA scientists. You can see all of our students and postdocs and staff in purple shirts around. They will be there to talk to you, answer questions, tell you about anything you want to know about. And then every 15 minutes, there will be tours leaving for Dearborn Observatory. So if you've never visited Dearborn Observatory, you certainly will have the opportunity to tonight. Those of you who know how to get to Dearborn, you can certainly go over there and the tours will show up afterwards. But please do take advantage of that opportunity. Let's see. There will be a survey afterward. And if you fill that out, we like feedback about the events, about how you like them and things that we can do better to make the experience more beneficial for you. If you do fill out the survey, there will be an opportunity to win this print up here to impress your friends who come to your house for barbecues, your astronomy print hanging in your art collection at home. So if you fill out the survey, we will enter your name for that. If you don't want to do any of the stuff I've described, you can stay in here and play astronomy trivia afterwards, and there will be CIERA swag for the winners of that. Okay? Okay, so without further ado, let me introduce our speaker for tonight. Tonight, we are very pleased to feature Dr. Caitlin Witt. Caitlin is a joint postdoctoral fellow with us and the Adler Planetarium. She is an expert in many things: gravitational waves, something called active galactic nuclei, which are giant black holes in the centers of galaxies. She's interested in big data, but she also has a very strong streak of interest in public science, which is why we're featuring her tonight. She does a lot of work at Adler with their public observing program at the Dome Observatory, and she does lectures of the sort that you're going to hear tonight. So these are certainly a great pleasure to introduce and welcome her. I promised her that I would not embarrass her, but she told me I should tell you the title of her thesis. Okay, so when we do our PhD, we have to write this big fat book of all the cool science we did to earn our PhD. So Caitlin's thesis is the kind that you tell your mother to impress them what you did in grad school, and then it gets very good at the end. So the title of her thesis was Bayesian Methods for Multi-Messenger Astronomy of Supermassive Black Hole Binaries, Pulsars and Quasars and Gravitational Waves. Oh my. So, without further ado, Dr. Caitlin Witt.
Hello. Thank you so much for the lovely introduction. What I forgot to tell Shane that I think all of you might find interesting is that I'm originally from Illinois. I looped around for college, went to New York State, West Virginia for grad school, and then I'm so happy to have made this stop back home for this postdoc because I get to talk to all of you when I am from right down the road. So yeah, today I'm going to be talking to you all about what I have given the lovely title, Tuning into the Cosmic Symphony, Pulsars, the Gravitational Wave Background, and beyond. And the important thing to get out of the way if anybody has a question, I want to make sure everything is clear, all of your questions are answered, everybody leaves happy and having learned something interesting. So if you have a question, we will have a microphone going around at the end of the talk, so you can ask your question live. But if, like me, you are notorious for forgetting questions soon after you think of them, and you want to just get it out of the way and submit it, there's a form here. You can submit your question. If your question gets answered during the talk, great. And if not, it will be prioritized later along with the live question, so you don't have to remember it for 40 whole minutes. So I'll wait to see any phones go away. Okay, I saw them all go down. Ooh, one more. I'll wait for you. Okay. So, to get started, here we are in the Milky Way galaxy. If you drop a Google Map pin on here, on the scale that this talk is relevant today, this is us. This is home. This is your home address, right there at the sun. And we are nestled safely within a spiral arm of the Milky Way, nice and happy. But lurking nearly 24,000 light years away from us, in this bright spot at the center of our galaxy, there's a monster. For a very long time, we weren't actually able to see that monster. We knew that there must be one there because we saw supermassive black holes, or the evidence of them, in the centers of other galaxies. Our galaxy isn't unique. If they're out there, why not in ours? And it wasn't until we saw evidence of the stars moving around something very, very massive that we were actually saying, oh, it must be a supermassive black hole. And eventually, even later, we were able to take a photo of our own little monster, Sagittarius A star. And like I mentioned, most galaxies out in the universe have supermassive black holes within them. And the other interesting thing about the universe and about galaxies is that galaxies are not islands. We've learned that there is a whole universe of them outside of our Milky Way. Almost every dot you can see in this image here is in fact a galaxy. Nearly all of them have a supermassive black hole lurking at their center. And as you can see, those galaxies are not widely separated at times. Here we have 4 of them in close proximity, and things evolve over time. What do you think might happen if these things are near each other? Yeah, I see hands. Good job. This will even happen close to home. It's in fact true that someday the Milky Way, our nice, safe little home, will collide with the Andromeda Galaxy, one of our nearest neighbors. So don't worry, this isn't going to happen for a very, very, very long time, but it's already in the process of happening. And 2 of the major players in this story are not just the galaxies themselves, but those monstrous supermassive black holes at their center. So when galaxies merge, it is actually quite a long process. You can see here in this visualization, as the galaxies come together, the stars scatter off into space, the cores start to get disturbed, and it takes time for those dense cores of stars at the middle to come together and then eventually settle down. So a question you might ask, thinking, okay, each of these galaxies had a monster at the center. What happens to them now that this galaxy has merged and it's sitting there visibly still? What happens is their black holes also slowly inch closer together. So those 2 monsters may be of different sizes, different levels of activity, will gradually sink to the center of that newly formed galaxy and eventually get close enough together to interact. When that happens, we call this newly formed system a supermassive black hole binary. So you can see 2 supermassive black holes here orbiting each other, forming a duo, rather than 2 independent supermassive black holes out in their own galaxies. When this happens, as you might have guessed from the title of my talk, these things can emit these things called gravitational waves, which I'll tell you all a little bit about. So, before we get into what is gravitational waves, I want to start with just a few definitions of what a wave is. This is something we're all really familiar with. We see waves on the oceans. We hear sound waves in our day-to-day lives and in our voices. You're hearing me right now. There's a few terms that make it really helpful to compare different waves. The first is a wavelength. This is physically how big a wave is between troughs and peaks in the wave. So one wave crashes on the ocean. When you see back to the next one, that's a wavelength. Might also be helpful to define a similar quantity called the period. This is measured in time. How long is it between crashes of the waves breaking on the shore? Another way to describe this is in terms of a frequency. This is just how many waves per second there are, how many crashes per second. For waves on the ocean, that might be a low number. You wouldn't expect many, many crashes per second, right? You kind of have an intuition for how often ocean waves come. But this is kind of the thing that says, okay, if we have a sound wave, what differentiates a low-pitched tone from a high-pitched tone? That's a frequency. I'm not going to sing for you, don't worry. Okay, so we have our wave definitions, but what makes a gravitational wave? The best way to describe this is start with a gravitational wave source. Here, I've drawn us a nice little black hole binary. They're orbiting around each other, doing a merry little dance. If you look very closely, one is saying we. And then we have a ring of masses arrayed somewhere along our line of sight between our gravitational wave source and us here on Earth observing them. Maybe they're stars, maybe they're something heavier, something heavy. And at the start of our wave, they're arrayed in a circle. As our wave continues past us, gravitational waves are going to deform space itself as measured by masses sitting on that fabric of space-time. In one direction, they'll squeeze those masses in that space closer together, and in another direction, they'll stretch it apart. As the wave continues cycling, it'll return to a circle, and then as it continues on, it'll stretch and squeeze in the other way. The vertical axis you see is now squeezed, the other axis is now stretched. If we were to play this over time as a movie, as our wave repeats and repeats and repeats, we'll see this very unique stretching and squeezing motion on our array of test masses that are sitting out in that gravitational wave deformed space-time. This is the unique signature of seeing a gravitational wave, this repetitive pattern. So if we were driving along the road and they wanted to tell us, there's bumps in the space-time ahead, this might be a caution sign that we would see, the unique signature of gravitational waves. There are quite a few things that produce gravitational waves out in the universe, but they all kind of have some similar quantities, namely that they're heavy and that they're dense and they're moving around each other. So here I've shown a few of them, and they're all pairs of compact objects. So one might be pairs of small black holes, or bigger black holes, or even supermassive black holes. But you can see they span a very wide range of frequencies, all the way up from where if they were sound waves, you might be able to hear them with your ear, all the way down to waves that are so long, they take decades to pass. The only gravitational waves we have detected until the past year have been from one category of these gravitational wave sources, the very smallest kind, the ones that were formed by the deaths of stars. I like to compare those to, if we have a string quartet, those gravitational waves that we've detected so far are only violins and violas. We have not heard any cellos. We have not heard any stand-up basses. So it wouldn't really be complete, right? Unless we were looking for those lower notes to really round things out and give us a full picture of what was out there. Similar to the way that we need different types of telescopes to look for different types of light. For example, the Hubble Space Telescope cannot see the same types of light that radio telescopes can. We just need those different instruments to get a full picture of what's going on out there in space. That's because those electromagnetic waves are separated in wide ranges of frequencies. But we need those different types of detectors to be able to see the different waves. The same is true of gravitational waves. Because these things are so widely separated in frequency, they're deforming space-time in such different ways, we need completely different types of detectors to actually be able to measure that very subtle stretch and squeeze motion as it passes by the Earth. So some are based on the ground, some future ones will be based in space, and the one that I'll be talking about specifically today happens to be the size of the entire galaxy. So if we return to our happy little black hole friends doing their merry little dance near their circle of stars, maybe we can focus on just 2 of those stars, maybe along the directions that we were picturing before, those axes where the gravitational wave stretches and squeezes space-time. If we happen to construct a device that had some heavy things on those 2 perpendicular axes, maybe some very heavy mirrors with a laser in the middle, this might be a type of device that would actually be able to see that stretch and squeeze as our wave repeats. This is an example of a ground-based gravitational wave detector that's made of a laser interferometer. It sees the difference in that stretch and squeeze of the arms as the mirrors move and are affected by gravity. But something like this, while it can see that road sign, that signature of gravitational radiation, it will never be able to see a wave that is decades long in period or is almost a light year long in wavelength. It's much too small. Instead, we have to think a little bit bigger. And we return to our nice little home, the Milky Way, and we'll look and see near our nice little Google Map pin showing where we are, some convenient little objects scattered throughout the Milky Way that will give us a hand and serve as our test masses. Rather than mirrors, we're going to use things called pulsars. So when our gravitational wave passes, they're at the right scale to be sensing that stretching and squeezing. So they can actually detect as the gravitational wave passes. So this particular objects that we're going to be used are called millisecond pulsars. These are neutron stars that are the remnants of a dead, very massive star. They're essentially as dense as an atomic nucleus, and they have very, very strong magnetic fields. What that causes is a beam of radio light to come out from their magnetic pole, akin to our North Pole. When that beam spins around and comes across our line of sight, if it points directly at us, we see a flash. Ordinarily, we wouldn't be able to see any light from the pulsar's surface, only when the beam points at us. I like to describe these as cosmic lighthouses because it's a similar effect. A ship far out at shore won't see the lighthouse when the beam is not pointed directly at it, but when it points in its direction, it's able to see the blinking. So if we sum up the light our telescope can see over time, we'll see nothing, 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 bing. And then over time, that will repeat, tick, tick, tick. Sounds almost like a clock. So, as I said, these are the end stages of stellar evolution. We take a massive star, we let it go through its supergiant stage, it gets red, it blows up all its layers, it gets really large, and eventually it goes supernova. That stellar core can become a neutron star. So that's one wild thing that they do. Another is that these millisecond pulsars aren't just garden variety pulsars. To get to be spinning so fast on the order of milliseconds, which happens to be faster than your kitchen blender, they actually have to nibble a little of material off of a companion star. They just suck a little bit of its atmosphere off. And by doing that, it yanks a little bit of material and helps itself spin faster, like it's being revved up. So these go from spinning about once a second to once a millisecond, so 1,000 times as fast. And these things also just happen to be about the size of a city. So here is a lovely illustration of a neutron star hovering over the skyline of Chicago. Of course, Chicago would probably not look so peaceful if there were really a neutron star hovering so close. All of our credit cards will probably be wiped, or we'd be stretched apart by gravity, but that's okay. It's just having a nice time. But you can imagine, okay, this thing is huge. It's this mass of a sun. It's the size of a city, and it's spinning faster than the blender in my kitchen. This thing can't be stable, right? It must sound like it's going to blow itself apart. Actually, instead of being unstable, they're actually some of the most stable objects we know of. So much so that that nice little tick that we can imagine as our lighthouse comes around, at times has been able to be timed with enough precision to rival atomic clocks. Until atomic clock technology, pulsars were actually better. They're some of the best clocks that we know. They're this cosmic gift that are existing out in the universe just waiting for us to observe them. So if instead of looking at this tick going as a movie, maybe we could line these ticks up and say, okay, one pulse on the top, the next pulse on the bottom, the next pulse on the bottom, and so on and so forth. If the clock ticks were perfect, every rotation was exactly the same, we would see them all line up perfectly straight. Of course, these things are natural, they can't be perfect, so there is some little bit of variation from pulse to pulse or clock tick to clock tick. This is where we need to time very carefully. If we time a pulsar over many, many rotations, what will end up happening is we record known by the name of unknown pleasures, and we come up with a rock and roll album. Not actually, but this album cover is actually real pulsar data. It's from the Pulsar B 1919 plus 21. That's where it is on the sky. And that was the first pulsar ever discovered by a wonderful scientist known as Jocelyn Bell. So if you ever find this album, give it a listen, but also look at the cover, because pulsar astronomers love it dearly.
Spins, that beam might actually get swung into our line of sight, kind of like a lighthouse. And whenever that beam's...
Oh, that's Steve's voice. Well, I don't know how to fix that. Imagine you can see pulsars up there and Steve's not yelling at you. Okay, so we have our array of pulsars, and we have learned a bit about gravitational waves, but it's also important to talk about how we actually observe them. And the way that we do that is with giant radio telescopes. So the first one that we use is Green Bank Radio Telescope, West Virginia. The next was Arecibo in Puerto Rico. Then we also used the Very Large Array in New Mexico. And finally, the Chime Radio Telescope in Canada. When we put all of these telescopes together, we can observe pulsars better than we could with one telescope alone. We can observe them over the course of the year at different radio wavelengths and learn more about them than we ever could by just looking at them every once in a while. There's a special group that has come together to actually get time on all of these telescopes and to analyze all of that data that I'm going to talk a lot about today. That group is known as NanoGrav. It's my research collaboration. NanoGrav is the North American Nanohertz Observatory for Gravitational Waves, which is a bunch of convoluted words, but we do actually already know basically everything we need to know to understand the title. All the telescopes are in North America. We're looking at low frequencies. That's what nanohertz means. We're using observatories, and we're using those pulsars as an observatory to see these things called gravitational waves. So we like to say NanoGrav uses the world's largest radio telescopes to measure pulses from scores of pulsars, each spinning hundreds of times a second, and together make a galactic scale gravitational wave detector. They detect Earth bobbing on a sea of gravitational waves, all emitted by gargantuan black hole binaries in the centers of colliding galaxies scattered throughout the universe, which is a big undertaking. But to bring things back into scale, I also like to remind everyone that NanoGrav is also a group of people. You can see them all there, or at least a good fraction of us. And we are a group of radio astronomers, pulsar astronomers, gravitational wave astrophysicists, computational physicists, data scientists, and time domain astronomers, and more than 100 institutions. Since we took this picture, we've probably more than doubled. But what I do want to emphasize is that all of that work that I showed on the previous slide really does take a village, and it takes a pretty widespread village. So it really couldn't be done without all of these people and all of their hard work. So I do want to acknowledge them. Okay. All of these people, we do our observations, but what does that data actually look like? So over time, we observe pulsars again and again. And over time, we've released that data so the scientific community can use it. Our first data set was 5 years long, and it had 17 pulsars in it. And each dot on this graphic is a single observation of a pulsar. So you can see each pulsar is side to side, each time span is vertical. And different colors refer to different telescopes. Our next data set was 9 years long. It had 37 pulsars. We added 20. Following one was 11 years long. We added 8 to make 45 pulsars. The next data set was soon after. It was 12 and a half years long. We only added 2 pulsars. And our most recent data set, the one we're going to talk about today, was 15 years long. It contains 68 pulsars. We added 21 since the past data set, so just think about how much work we did in those 2.5 years. And what I think is really interesting about this plot is you can see some structure of when the observations were taken or not taken, especially when you think about which telescopes they are. For example, you know, green points cut off at a certain date. Green Bank broke a wheel, so we couldn't use it for a summer. It's very rude. We also found a technology issue at Arecibo during this time span that also coincided with Hurricane Maria. So part of the data had to be excised because we found that error, but also this is when the telescope was not observing. And this end date, unfortunately, is the date that we lost Arecibo. Arecibo collapsed in 2020. So we decided to go ahead and use all of its data that it could give us. But luckily, it will always live on in this data set. We never throw out data. And you can see how all of the previous observations are included in every subsequent data set. So while some people like to say, well, you don't really use Arecibo anymore, we always will. So as of today, Nanograv has observed 79 pulsars, some of which are not even in a data set yet, for a total of over 500,000 times of arrival. Those are individual pulses, using now 4 telescopes over 15 years. So when people ask what the secret is to detecting gravitational waves with pulsars, I will always tell them, just like comedy, the secret is timing. The other very important thing to remember is that each pulsar is, in fact, unique. While they are really wonderful clocks and compared to, your ordinary run-of-the-mill astronomical object, they are very stable. They do all act a little bit differently. So things that are orbiting them, or such as, a mass the size of Mars, might induce a change. So if we were to say, if we remember back to when we lined up all our pulsar pulses vertically, we flipped that on its side, we said each pulse and lined it up as a point here. If it's timed perfectly, that difference will be 0. If it's timed imperfectly, which it always is, there will be a little bit of scatter. If there's structure, we might be able to fit something out and model something about the pulsar. For example, some kind of an error in how we measure how fast it's spinning. We might measure an error in where it's located on the sky. We might measure it moving. We might measure a companion orbiting around it. All of these things we can subtract out of the data and get a good timing model where we account for the spin rate, the orbit, any motion, or noisy imperfections. One fact that I like to share about just how powerful our pulsar timing array is to measure solar system variations is that until the Juno Observatory arrived at Jupiter, Nanograv knew the orbit of Jupiter better than NASA did. NASA has the lucky ability of having spacecraft with cameras on it, and it turns out once they launch it in generally the right direction, they can turn that camera on and do a little bit of steering. We don't have that luxury, so we need to know exactly where the center of mass of the solar system is, to as precise accuracy as we can. The biggest draw on that center of mass, besides the sun, happens to be Jupiter, which is why we had to learn so much about its orbit to get to where we are today. So, we have our array of pulsars. Each of them is ticking along very nicely or not so nicely, depending on how it's behaving that day. And then we say, okay, what if a gravitational wave comes along? We can use these pulsars together to look for things that affect the galaxy as a whole, such like gravitational waves or any large-scale motion. can also look for things that affect the Earth itself, such as solar system objects. This is why we were so sensitive to Jupiter. Okay, so let's think about that gravitational wave thing a little bit more. So we've talked about supermassive black hole binaries. We've talked about how gravitational waves affect space. We've talked about pulsars. And we've talked about how we observe them from the Earth. So does everybody feel ready to go and use a pulsar timing array to go look for gravitational waves? Yeah, okay. Not to throw a wrench in things, but there is one more thing to consider still. And that's the fact that, we really only talked about how to look for single gravitational waves from maybe an individual supermassive black hole binary. But all those galaxies I showed at the beginning, some had merged over in this direction, maybe some had merged over in this direction. We don't expect there to be just one supermassive black hole binary out there in the universe. In fact, we think there are many of them. We think this is a common occurrence in galactic history. So while there are gravitational waves from these individual supermassive black hole binaries, there's also, confusingly, a gravitational wave background made up of this cacophonous confluence of all of the gravitational waves in the entire universe, all sounding together. A way I like to describe this that feels a little bit more down to earth is we can think about a single gravitational wave as maybe a ripple on a very still pond. We can see it spreading out from its source, and we would be able to see exactly where it came from. We know what it looks like. However, if there are multiple sources causing these ripples, maybe it's raining a little bit on our very, very still pond, we can see numerous ripples. They're all overlapping. They're all different sizes. But we can still actually pick out the individual droplets that are making them. There's not too many yet that we can't tell them apart. This is sort of like supermassive black hole binaries. Some of them might be at slightly different frequencies. There might be slightly more of some types than the other, but we can count them up. And we would see gravitational waves from each of them. This is sort of akin to, if we go back to our bass analogy, okay, we have a couple bass players in the room. Some of them are playing very low notes, but the basses can play slightly different notes. Some can play at the top of their register. They're still basses, but they are playing slightly different notes. They're all adding together. Now imagine we go see the ocean. Can we see the individual waves that make up the rough chop that's far out at sea? I see shaking heads, good. We can't tell where any of those waves are coming from, what direction they're going, or how strong they are. We can only see the overarching picture. This is akin to, okay, if we have our supermassive black hole binaries that we can look for with our pulsar timing array, if there's few enough of them, remember, we can maybe try and start to stack them up and see them individually. But once there's enough of them, those individuals fade into the background. And instead, we can only see the sum strength of this gravitational wave background signal that I've drawn and represented here with this black line. You can see it's distributed over frequency, and it has a unique shape, but we can't see the individual components that make it up anymore. What do we call this? Actually, once it's distributed over frequency like this, we call this a noise signal. We don't see the individual waves, we just see random noise. And because it has this unique shape, we call this red noise. I'll unmute my computer now and show a quick example. Do you hear it? It's very low, right? It's rumbling. That's the red term in it. There's more low notes than high notes. Okay, we'll come back to this. Many of you might have heard of white noise before. That's kind of like what we described as the noise that's on our sleep machine, or like a droning noise like the cicadas we're going to hear later this summer. That does not have that same structure, that same shape to it. It's uniform across all frequencies. That sounds a little bit different. Hear the difference? It's higher. It's more spread out. It sounds a little bit like the ocean or a sleep machine, less like cicadas. I'm going to go back back to the red noise just to compare. The rumble. Do you hear the difference? I described this the other day as, okay, if we had our cicada drone, but there were also lots of very, very large cicadas making very long wavelength sounds. Luckily, that won't happen this summer. We're just going to have normal ones. It'll be okay. Okay. I'm actually going to go back. Okay. So the first thing we're going to look for gravitational wave background is looking for this red noise process. That is clue number 1. Remember that. However, there is one other thing that we need to remember. This microphone, come here. Louder now? No, it's not loud. I'm trying to make myself louder. How's that? Better? Yeah. Okay, good. So the one thing we need to remember is that unlike a gravitational wave detector that is here on Earth, where we only have 2 points, our pulsars are scattered throughout the galaxy, and as we're observing them from Earth, they're scattered across the sky. And as our gravitational wave passes, we need to think about how it's going to affect each of them, as well as the Earth here. So as we observe multiple pulsars, we can compare where they are in the sky and then see how similar that noise term is in each of them. So without gravitational waves, we wouldn't expect any similarity when we observe each of our pulsars and compare where they are on the sky. But when gravitational waves are passing, when there's a gravitational wave background rumbling in the distance under our pulsar timing array data, when we look at each of our pulsars compared to where they are in the sky and how close they are together, we expect there to be some similarity in each of those noise rumbles in each pulsar's data set. So this is clue number 2. This is our road sign that we're looking for gravitational waves. And when we went to analyze our 15-year data set, this is what we saw in the yellow points. You can see, even by eye, you can start to see that particular pattern that is giving us our road sign, our warning sign, that there's gravitational waves here. There's going to be gravitational radiation ahead. So, what did we do? Of course, we're astronomers, so we all banded together and we wrote a paper. In fact, we actually wrote about 10 papers. And you can see all those people that I showed before, they show up on this list. Again, I wanted to acknowledge them. It's people who did this really wonderful work. But if you scroll down through this paper and go to the very first figure, this is what you'll see. And I want to highlight that this very first figure, we already know how to decipher it. We can see that on the left, we are starting to see that red noise, that summed effect of these gravitational wave sources emitting gravitational waves, more at low frequencies, here on the left, and less at high frequencies, making this red sloped pattern. Is this working? Yeah, it is. It looks familiar, right? That's sign number 1. And then sign number 2 is in our data set, when we compare our pulsars against each other, we see this unique correlation pattern that says, okay, you saw the noise, this is our evidence for gravitational waves. So we see both the noise, we see the gravitational waves, and what this means is that we now have evidence for a gravitational wave background. Cue air horns, excitement. So last summer, some of you may have seen some news about this. There were some newspaper articles. There were some lovely videos produced that went around the internet that explained all of what I'm talking about today. Some of my friends in Nanograv were on a panel at the National Science Foundation telling the world about what we had found. And this was really exciting. But I want to emphasize that while this is, the culmination of 15 years of work and even more for people who did all the background and developed all the methods that we used, this is not the end of the road. We have found our 2 pieces of evidence looking for a gravitational wave background from low frequency gravitational waves, but there's still more science yet to come. if we just look at what we found in the 15-year data set, there's still more that we can learn from this noise spectrum. While it's consistent with this noise spectrum from supermassive black hole binaries, it's also consistent with a gravitational wave spectrum from other things. This could be from inflation from the Big Bang, or cosmic strings, or inflationary physics, lots of things. And the way we'll learn about this is by learning more and more about what shape this spectrum takes as we get more and more data. We'll be able to measure it better and better, and then hopefully someday pinpoint exactly what is causing the gravitational waves that we're starting to hear. We'll also be able to tell, okay, are we seeing just gravitational waves? Or is there anything else we're seeing in this low frequency noise spectrum? If it is binaries, there's some other things that can cause them to merge a little bit faster, like the gas and dust and stars around them. And we'll be able to see that as we measure the spectrum over many years to come. Okay. The next thing that will be interesting as we get more data is, okay, we're starting to see the ocean. We remember this. But we do want to think back to our ripples. What if we can see those individual gravitational waves someday? The unique thing is that now we know the ocean is there. Instead of looking for a ripple on a very still pond, we're looking for a ripple on the ocean. So we need to work a little bit harder to actually disentangle them and pick out that ripple. This will be especially true someday when we can see multiple ripples on top of that ocean. We won't be able to do that unless we keep timing pulsars and keep developing methods to actually disentangle these signals. Someday, one of my favorite aspects is that if we do see one of these individual gravitational waves from a particular supermassive black hole binary, we may also be able to see it with a light-observing telescope. The galaxy it's hosted in might tell us that there's something going on in its center, and we might be able to pair that information up with its gravitational wave signature. We call this multi-messenger astronomy, where we're using both light and gravitational waves together. But again, this won't work unless we keep timing pulsars, keep searching for gravitational waves, and keep observing galaxies with large surveys and new telescopes. Okay. So over the course of this talk, we've learned a lot about supermassive black hole binaries, the pulsars, and the radio telescopes that observe them, as well as the scientists who look for them and do all of those steps. But if you're still asking, why is there so much fuss about this? I'll tell you that the history of the universe is written in the symphony of low-frequency gravitational waves, and we're finally starting to hear it. Thank you.
Okay, so we're going to go ahead and take some time for questions. We have folks with mics who are running. We'll run the mic to you. We do have folks listening online, so if you can please wait for the microphone to arrive, that would be helpful. And then, Monica, you're monitoring questions online for me? Okay, so I will look at you periodically as well. So we have 10 to 15 minutes for questions, so please let us know what you're thinking about.
Yeah, it's that.
Hi, thank you for coming. My question was, how do black holes work?
Ooh, that's a spectacular question. Jen, can you wave for where the question was? There? Okay, I wanted to look at you. Okay, the basic idea between how black holes work is, imagine taking a lot of stuff and compressing it smaller than you can imagine seeing. It's both heavy, but it's dense, but it also kind of breaks normal physics. We expect how, something that's heavy and has a size to work. Black holes don't have a size. They only have a size in how they affect light, and we can only measure them from their mass. That's kind of my explanation for how black holes work, but really the answer is we don't really know. We have mathematical descriptions for how they affect the things around them, but we don't know what's inside.
How many stations are you having that's covering the sky at night? Or are they basically just covering I'll call the northern hemispheres versus the southern hemisphere?
Ooh, that's a good question. So I think you picked up on an important quality, is that all of our telescopes that we use in nanograv are based in North America, so we can only see what they can see. Our lowest latitude telescope is the Very Large Array, and we're lucky that those telescopes can actually point down pretty far, and they can see our farthest south pulsar that is decently far south. So we can see a little bit of the southern sky, but we can't see it all. So this is where we actually turn to our international friends, particularly those in Australia, who have a great view of the southern sky. So while we can see gravitational waves coming from anywhere through that galaxy, because they affect pulsars that are scattered throughout the sky, it does behoove us to work together. And pulsar astronomers have formed an international collaboration called the International Pulsar Timing Array. And we all put all our data together to try and see more gravitational waves that we couldn't alone.
All right, we got a question over here now.
Thank you for a fabulous talk. That was very interesting and fun. So please correct me if my presumptions are wrong. If I'm recalling, weight is a property of mass and gravity, correct? So could changes in weight, even like as subtle as they are, be used as a variable to measure gravitational waves, at least theoretically?
Yeah, okay, so weight from a scientific perspective, yeah, like you said, is coupled gravity and mass. So like my weight, if I were standing on Mars, would be a little bit different. But I think, I'm trying to make sure I describe this accurately. I think the important thing is that you need to see the motion. While the gravitational wave is affecting space-time, it's not changing the mass of the planet that I'm standing on that causes that gravitational field to make the weight change. Instead, we need the two test masses to see how their relative positions are changing, because it's changing the space itself rather than, it's making gravity a little bit stronger or a little bit weaker. Does that answer your question?
Yes, thank you.
Thanks. I have a general idea, but what happens when the black holes merge?
I think what I'll say is that both a lot of things happen, and we also don't know exactly what happens, because we haven't seen this happen before. We've seen it happen with little black holes, and what happens there is that they come together, they release some energy, and they also just permanently warp space-time around them, which is actually very cool. So if we were to see two supermassive black holes merge together, we expect they would throw out a lot of energy in the form of gravitational waves, but they would also distort the space around them permanently. And we would maybe be able to see that if we were very lucky.
What would happen to us?
What would happen to us? Luckily, these things are so far away that while they do affect Earth, it's incredibly, incredibly small. It's a much smaller distortion than you would ever see or feel. If there were one, in our backyard, we might feel a little bit of wobbling, but luckily we know that there's not. So we're okay.
So, what would happen if what happens when a neutron star dies?
What happens when a neutron star dies? Ooh. I only know how to answer this question when a pulsar dies. So a pulsar, remember, is a special type of neutron star. It's one that is sending out this beam, and we see it across our radio telescope. But these things are spinning, and while they are very stable, they do lose a little bit of energy. They lose momentum. Like if you're spinning a top, it stays stable for a long time, but eventually it can't hold itself up anymore. The same goes for these neutron stars. They do slow down. Eventually they'll stop their blinking. But what happens to that cooling remnant, we can't really observe yet.
Caitlin, this is a response that we got from the Google form, and it says, "You're so cool. How did you get interested in this topic?"
This is an excellent question, because I actually have an answer. It's not just, I walked in someday. I actually started my astronomy research career researching exoplanets. So I thought, oh my God, exoplanets, this must be the most important thing anybody could ever learn. And it turns out that when you study exoplanet atmospheres, you need to learn a lot of chemistry. And I'm not very good at chemistry. And then I saw a news article about a professor at my college describing the idea of nanograph. And I thought, what a wonderful, incredible experiment that is so simple that I can't imagine how anybody could have ever come up with this. So I sent him an email, and I started working on nanograph research, and I just didn't stop.
We got a question up here again.
Yeah, I'm sorry if I missed this during the presentation, but how do gravitational waves cause pulsars to spin specifically? Because if it's just a pulse of gravitational energy coming in and out, wouldn't it just cause it to wiggle around?
Yeah, you're exactly right. Yeah, I think that's something that wasn't very clear that I described. So, imagine back to our ring of stars at the beginning. It's moving those masses around. But what happens is that those rings of masses are at sometimes in the wave a little bit farther from the center, and it's sometimes a little bit closer. So when that's a pulsar, and there's just a chain of bright pulses coming closer and closer to us, closer to our radio telescope, they're flashing and flashing, and then we see the pulses getting closer and closer. We see one at a time. Those are either traveling over a little bit less space or a little bit more space. And then as that repeats, they're coming a little bit early or a little bit late, or a little bit early or a little bit late. And so that's the effect of the gravitational
wave. It's kind of like the Doppler effect?
Kind of, yeah. Similar. It's more that's a good description. But they're a little bit early, a little bit late, rather than changing in frequency.
Got it.
Hi, Caitlin. Hi. Thank you so much. It was such an interesting presentation. I have a question I don't understand very well. What do you learn from these gravitational waves? How can you apply? And I guess a related question is, just when you show the ripple where all of the drops of rain are coming and creating all of these all of these waves and ripples, wouldn't they cancel each other out at some point? So what are you learning?
Yeah.
Sorry.
No, it's really good question. So I'm just going to go back in the slides to the picture. So we can look at this one. Yeah, at some points, you can even see in this picture, where's my laser pointer? So here, where there's these two strong ripples coming together, you can see at some points they're adding together and at some points they're canceling out. The same is true when we're thinking about our ocean. The points on, where there's a strong piece of chop is where they're adding together, and then the weak nothing is where they're canceling each other out. That's absolutely true. And, the only reason we can see this gravitational wave background at all is that they're affecting the Earth, and we're seeing how the Earth jostles around between all of our pulsars. That's also affecting the pulsars, but we would never know what to expect if it's canceling or adding at the pulsars. And then as for what we expect to learn, I think it goes back to, A, what is causing it? Is it some kind of early universe effect that affects how our universe grew from the Big Bang, or how it interacts at the deepest level, or is it supermassive black hole binaries? If it's binaries, which I certainly hope it is, just because I'm a binary astrophysicist, but I don't want to be biased. But it tells us things like, the strength of that noise, how loud it is, tells us something like how many of them are there. Do we think galaxies merge often or rarely? Do we think there's things in their environments that help them come together? Or is there not enough stuff in the middle of galaxies to actually get them to that point? So we've heard a background, which means there must be something out there that's interesting, but we still need to tell the source, and depending on what it is, we need to learn exactly what is causing it.
All right, we have a question over here.
Thank you. So have we ever observed like more than 3 black holes like spinning together? Or including 3?
I think I've heard like ideas for having triples, but certainly not of supermassive black holes. I think there's ideas of seeing, one is wandering off. What if it's because it merged with another one and got kicked out, or things like that. But generally the idea is that we think binaries are out there in the universe. We think another one coming in would be a little bit more rare and also quite unstable. So while these two can stay together in orbit for quite a long time, one coming in would kind of disrupt the whole thing. So while, I'm sure there's people in this room who work on stellar mass black holes who might know a little bit more about triple systems. It's not something that's in my specialty, but my general impression is that we think they're rare.
This is another question from the Google form. Why do neutron stars produce radio waves, and why do these waves only come out of the poles?
Yeah. Oh my God, such a good question. So the general idea is that it has to do with the magnetic field of the neutron star. And these things are very, very magnetic. Order of thousands of times more magnetic than the sun. And it has to do with these things were stars. They were a certain amount of magnetic, and then you shrunk it, but kept all that magnetism. So now it's denser. So these things have these very impressive magnetic fields, so magnetic that those field lines, I'm going to use like some magnetism terms just to do my best, they're open at the poles, which means that they're very directed. So if, stuff or particles come in, they will end up moving around at the poles of the neutron star, at like the north and south pole of the magnet. And that is why we get these radio waves. It has to do with stuff spiraling around the light wave or the magnetic field lines. What is actually interesting is that pulsars are bright in radio, but they can also be bright in other wavelengths. We actually can see a lot of them in X-rays. So there's an X-ray telescope mounted on the International Space the International Space Station called NICER. I don't remember what NICER stands for right now, I'm sorry. But it observes pulsars in X-rays, and it can actually time them and make an X-ray pulsar timing array to do similar things that nanograph can.
Okay. It melts our hearts to answer any questions. We're going to take 2 more. Okay. Okay, and then Caitlin will be outside at the Ask a Scientist table, and we would like you to please engage with her there. So let's take the last 2. So we'll take one here and one to Leanne, and then we'll adjourn outside.
I know you didn't really cover it here, but I was wondering, how does a black hole become a quasar? Or a black hole or supermassive black hole, how does it become a quasar?
Such a good question. You throw stuff in it. So if we have our black hole, and galactic centers are busy places. There's lots of stuff in there. But eventually, the black hole might actually have something fall onto it. What we call that is accreting. It means stuff is like gradually falling onto it. And what happens is, black holes are very good at eating things, but they're not perfect, and sometimes they burp out stuff and light. And what happens is that stuff and light ends up coming out in a jet, and that's when that black hole is active, it's actively eating, it will end up sending out some light so we can see it. If it's not actively eating, we rarely can see it. And the way we see it has to do with what orientation that jet is in.
Do gravitational waves transmit through the universe at light speed?
Yes, they do.
One more question. Are pulsars uniformly distributed throughout the universe, or are there absence?
So they are not throughout the universe. They are throughout galaxies. Anywhere that in dead stars, there will be pulsars. But there are some places we find more of them. So we see them throughout the galaxy. And this is something that is quite important for us when we're observing, is that, they're throughout the galactic plane, but when we look across the sky, the galaxy isn't uniformly around us. The disk is in some direction. So we see more pulsars on one side of the sky than the other. And that makes, looking for gravitational waves a little bit hard because it's not uniformly centered around us. But then there are some places that it's common to find more pulsars. One is in places like globular clusters. These are big clumps of lots of older stars. There's lots of old stars. It means there's lots of dead stars. So you actually see lots of pulsars around there, too.
Well, thank you, everyone, for your attention.